In the last video, we looked at a very crude way of trying to answer this question, is there life out there? We were doing that by trying to calculate or estimate the exoplanet's surface temperature. And so before, we actually used this method. Okay, so I'll just say we used this method of just L is equal to 4 pi r squared sigma t to the fourth. But this is very crude. Okay, it didn't account for lots of things, but one of the main things is, the effect of, somehow the effect of an atmosphere, or even the color of the planet. And the main thing that really, when I say about the color, I talk about this term right here that's called albedo. So we're going to talk about that in just a second here. So this is what we were doing before. So what we're going to do then, we're going to do something sort of new, and we're going to still need the orbital radius that we were looking at before, but we're also going to need to know about the albedo. And so it helps to define that then. So A, that's called the albedo, and that is the ratio of, let's say here, reflected radiation to incident radiation. So here's what happens. Well, maybe I'll actually just write it as a fraction just so it looks easier. So in other words, A equals reflected light or power or energy, whatever you want to look at, divided by incident. In other words, incoming. This is how we define the albedo. So that means that the albedo has values between, if you reflect all of it, well then it's got the same amount of reflected as incident. So 1 over 1 would be 1. So that means, and if you reflected none of it, then you'd have 0 divided by 1, which is 0. So values between 0 to 1. And, well, actually maybe I'll say 0 and 1 so you don't think it's a minus here. So what we can do then, we can consider what happens on an exoplanet. And now, what affects the albedo? Lots of things. An atmosphere can, but so can just the color of it. And so that's why, the albedo is something that at least it attempts to do a better job of just being really crude and estimating the temperature this way. We're going to get a much better temperature estimate by using albedo here. But the albedo is affected by many different things. Just take a look at this little diagram to sort of have an idea what happens here on Earth. When here on Earth, we have a light coming in here. So from the sun, the light coming in, we'll consider that sort of incident light. That's what's coming in from the sun. And what happens? Lots of things. Some of the light bounces off directly from the clouds. So that's reflected light. So we'd have to count out this light right here that's reflected right from the clouds. But of course, some of that stuff hits, let's say, something that's really shiny. Let's say some ice or something like that, or something that's light colored. It bounces right off and comes out. So this is also reflected. And of course, some of it might hit dark things and actually be reabsorbed. Some of the infrared, for example, will be reabsorbed. And this is, in a sense, what happens with the greenhouse effect. That some of this radiation is actually sort of reabsorbed and re-emitted, so it sort of comes back in to sort of heat again, because all this, of course, heats the Earth. But when we consider the albedo, then we just consider, we don't care what happens in the bottom. See, it's sort of like trying to take into account everything that happens. Who cares? All we think of is what goes in compared to what comes out. Some of it might have bounced off the atmosphere. Some of it bounced off things on the surface. So albedo can take into account maybe you have an atmosphere or maybe you don't. If there's no atmosphere, then the color of this planet or the moon is going to have every effect. And if you have an atmosphere, well, then it's going to be the combination of things that are colors compared to things that are reflected from the atmosphere. And all sorts of complicated things can happen in the middle. But the idea behind albedo is just, who cares? We just look at how much is reflected compared to how much is incident. So here's an example of something that doesn't have a very thick atmosphere at all. It's called Enceladus. So this right here, this is, for example, one of Saturn's moons here. So this is Saturn's icy moon here. And so this one right here, it's very white, this one right here. In fact, it's pretty much all ice. So if it's very, very white, try to think about what would happen with the albedo. You have light coming in. Do you think most of it will bounce off the surface, off ice? I don't know if you've ever been on a glacier or looked at light shining from ice, but it's very, very bright because lots of the light shines and bounces off. So because of that then, because it's very white, because there's lots of ice, then we're going to have, lots of radiation reflected. This is the main thing here. So lots of reflected light is the result of this. And because there's lots of reflected light, that means the albedo, which is reflected over incident, will be then, we'll try to think about that then. If you reflect a lot of a light compared to what comes in, then you're going to have a fairly large value for albedo. So in this case, albedo might be, for example, as high as like 0.9. So that tells you this is something very white. So that's why I said, it takes into account, this method takes into account the atmosphere or the color. In a sense, it sort of does it all in one go and just says, who cares what the atmosphere is doing or what the color is? The result is the same. Right? If you have an atmosphere, maybe it absorbs some. Well, that will affect the albedo. That'll affect how much is reflected. In this case, because it doesn't really have much of an atmosphere, it has a tiny little one, but it doesn't have much. So because of that, its albedo is mainly due to just its color. And same thing then with something like Mercury. Mercury is very dark. That's the planet Mercury. And this is very dark. So that means then that there's very little reflection, because it's a very dark surface. Now, of course, there still is reflection. Sure, there is. If there wasn't reflection, we couldn't see this in a telescope. But I'm saying there's very little compared to something that was really icy, for example. Because there's little reflection, and the albedo then will be very small. So actually something like this right here might have an albedo of, something that's like 0.2, for example. So dark things have a low albedo, light things have a very high albedo in general. Well, then what we're going to do, we're going to try to estimate their surface temperature here. So what we're going to do then, this is going to be a little bit more complicated, but we're going to take it step by step here. So the very first thing we're going to do is we're going to assume, first of all, that the light emitted, in this case from the star, has a luminosity, in this case we're going to call it L star B. So this is sort of the first step. Second step, we're going to assume that the star is a black body. Remember what that means, to be a black body. And by the way, so is the planet. So what we mean here is that we can assume then that these are perfect emitters and absorbers of radiation. So that means we can use the Stefan-Boltzmann equation. In other words, we can use this equation that L equals 4 pi r squared sigma t to the fourth. This is the only way we had used before to estimate the temperature on the planet. But now we're going to use this as a starting point. Well then C, here's what we're doing next. So at an orbital distance, so we're going to sort of slowly take this piece by piece. So at an orbital distance d, let's say. Let's look at what happens here. So at this orbital distance d, we have the star. Here it is. And of course we have this distance out. So we have this planet that's sort of orbiting out at some distance. So this right here is the planet here. And we're out at some distance right here, d here. So what happens then is the light from the star goes out in all directions. This is the really, really important thing here, okay? Is that at this orbital distance d, so we'll say the light from star goes out in all directions. And because it goes out in all directions then, not all of it is received by the planet. This is the key thing here. So not all the light reaches the planet. In fact, There's only a fraction of it that does. And that's because a star's light is actually sort of spread out over this spherical shell. Remember, this is in 3 dimensions. I've done a really bad job of drawing a circle here, but it's really looking weird here. But the light from the star goes in all directions. Because of that, then, it goes out over a spherical shell. I mean, that's really what happens here. The light actually goes out in some sort of spherical shell. And so that means then we could say that this, this surface area of this spherical shell will be actually 4 pi times d squared. This is normally 4 pi r squared. That would be this. So that's only the part that actually reaches the planet. But it gets even worse. Because a planet only has the light, let's say, hit it on one hemisphere. Because of course this is a real life planet here. And because of that, the planet itself is some sort of sphere. And because it's a sphere, let's just draw it here. So this here is the planet. I mean, it's only got light that's actually hitting it on this side right here, on this front side. And that's because the back side of it will be all dark. So this will be, this will be the light coming in this way. So it only comes in on one hemisphere here, so only on sort of half of it. And that would have an effect of just pi times r squared here. That would be the size of the planet. So what I'm trying to show then is this right here, both of these right here will have an effect. And this effect will be that we're going to have what we call the absorbed light. So what I'm going to do then is sort of go down a little bit here and write this. So the light absorbed here, we're going to call it L, or the luminosity absorbed, is going to be equal to the luminosity of the star. So see, what we're talking about here is how much light actually reaches the planet. That's what L absorbed is. So maybe I'll say that. So L abs, that's going to be the power, let's say absorbed by the planet. And that's going to be in watts. And then we're going to have L star. Well, that's going to be the power emitted by the star. That's again in watts. My spelling isn't very nice here. So the main thing then to keep in mind is just this, that the power absorbed by the planet is going to be some fraction of what's actually emitted by the star. See, the star is kicking out light. Now the first thing was it's going in all directions. So I mean, we have this sort of effect here that it's going, there's only a piece of it that's actually reaching this planet in theory, and that's 4 pi d squared. Right? That's, depending on what distance it is. And then of that, we only have a fraction of that light which is actually hitting the planet. And that's depending on the size of the planet itself. So this would be just pi r squared, because that's just the area of a circle. If we look at this here from the front, that would be that. It would be just the area of a circle. You could also say, well, you take this thing right here and divide it by 2. But let's just take a look at this and just say, well, this is pi r squared. That's going to be the amount sort of hitting this area here, this front area. And so then what we can do is we can say this. We can write this fraction then. So it's going to be the pi r squared over 4 pi d squared. This is the sort of more complicated part. So this pi r squared, that's because that's the surface area of the planet that receives the light. This is where this sort of piece came from here. And this bottom part here, this 4 pi d squared, that became, that was actually because of the light from the star that reaches out a distance d. So that's the light from the star that reaches a distance d. And all this, though, we also want to consider what's actually absorbed. Remember, we were just talking about albedo. Albedo had to do with reflected light, but we want to know how much is absorbed. So we want sort of the opposite of albedo. Because if we just wanted albedo, that would be how much is reflected. But we don't want that. We want how much is actually incident. So because of that, we're going to have a term 1 minus a here. And that's just because we want absorbed, not the reflected light. So although that seems to get pretty complicated there, this is the sort of main equation we're working with here. So maybe we better define the other things here. We had r, that was the radius of the planet. And that would be in meters. We have d, that's the orbital radius of the planet. Again, that's going to be in meters. And the other thing we're going to need is A. A is going to be the albedo, which has no units. Albedo of the planet. So this could be something taking into account the color of the planet, you know, if it's a very light planet like Enceladus, or if it's a very dark planet like Mercury, or maybe this takes into account what the atmosphere ends up doing. So this is sort of this one term that ends up sort of, incorporating everything else. So this one equation right here, which may look really complicated now, I hope it becomes a little bit simpler to look at, because this is sort of the key, starting off with this. Now in the next video, I'm just going to continue it. We've done the hardest part. So in the next video, we're just going to put it all together and calculate or figure out how we can actually estimate the temperature.